Next is lesson 3.4, dispersion. Ordinary white light is a superposition of waves with wavelengths extending throughout the visible spectrum. The speed of light in vacuum is the same for all wavelengths, but the speed in a material substance is different for different wavelengths. Therefore, the index of refraction of a material depends on wavelength. The dependence of wave speed and index of refraction on wavelength is called dispersion. Dispersion is a relationship of wavelength and index of reflection or index of refraction. Figure 3.15 shows the variation of index of refraction n with wavelength for some common optical materials. Note that the horizontal axis of this figure is the wavelength of the light in vacuum, wavelength O or lambda O. The wavelength in the material is given by equation 3.5, lambda equals lambda O over n. In most materials, the value of n decreases with increasing wavelength and decreasing frequency. Thus, n increases with decreasing wavelength and increasing frequency. Intindihin niyo ba to? So, explain ko ha. The wavelength is equal to the wave of light in vacuum over the index of refraction. So from this figure, this is the wavelength in vacuum and this is the index of refraction. As in, for example, silicate flint glass, there's a curved line. So when the wavelength is, for example, 400, the index of refraction of the silicate flint glass is about 1.66. Okay? In here. In this figure. Okay. When the wavelength in vacuum is 450, like in this line, the index of refraction n of the silicate flint glass is somewhere in here, and that could be 1.65. Kalahati kasi ito, so 1.65. Okay? So this could be 1.64. Okay. Another example is itong si quartz. For example, 700 yung wavelength natin in vacuum. So the index of refraction of ni quartz is somewhere here in this line. So this is kalahati 1.55. It could be 1.54. So nag-a-apply dito yung wavelength is equals to the wave of light or the wavelength in the material. Wavelength in the material is equals to the wave of light, wavelength in vacuum, over the index of refraction. Figure 3.16 shows a ray of white light incident on a prism. The deviation or change of direction, change of direction, produced by the prism increases with increasing index of refraction and frequency and decreasing wavelength. Violet light is deviated most and red is deviated least. The other colors are in intermediate positions. So where's the sabi is violet light is deviated most and si red is deviated least. Okay? And other colors are intermediate positions. When it comes out of the prism, the light is spread out into a fan-shaped beam. So this is the fan-shaped beam. So this is the incident of light. Okay? So it should be reflecting somewhere in here. But since this is a prism, it reflects within a deviation or change of direction. So, si violet natin na light is deviated most kasi from this line, nandito masyado siya sa labas. And si red naman is deviated least kasi nandito siya sa pinakamalapit sa original line. The light is said to be dispersed into a spectrum. The amount of dispersion depends on the difference between the refractive indexes for violet light and for red light. And from figure 3.15, we can see that for a substance such as fluorite, the difference between the indexes of red and violet is small. What is fluorite? Fluorite. Sabi is the index between the violet and red is small lang ang difference. Kasi nga, dito lang siya and dito lang siya. A better choice of material for a prism whose purpose is to produce a spectrum would be silicate flint glass. Silicate flint glass. Bakit? Kasi malayo ang pagkakaiba nila, so they can make a much more broader fan. Ito, much more broader fan of light, for which there is a large difference in the value N between the red and violet. Okay? The brilliance of diamond is due in part of its unusually large refractive index. Another important factor is its large dispersion, which causes white light entering a diamond to emerge as a multicolored spectrum. Crystals of rutile and of strontium titanate, which can be produced synthetically, have about 8 times the dispersion of diamond. Produced synthetically. Ibig sabihin, they can be produced in a laboratory. Rainbows. When you experience the beauty of a rainbow, as in figure 3.17a, you are seeing the combined effects of dispersion, refraction, and reflection. Sunlight comes from behind you, and there's a water droplet, is partially reflected from the back surface of the droplet, and is refracted again upon existing the droplet. 3.17b. So the paths of light rays entering the upper half of raindrop. So this is the raindrop, and this is the down sun point. As it goes from the raindrop, as it enter the raindrop, it produces different light rays. Okay, ayan siya, different light rays, and the pattern of rays entering lower half of the drop is the same but flipped upside down. So, itong rays na to, yan na yung ating different colors of the rainbow. Okay. So, yung water droplet natin as a whole, kaya nga nagkakaroon lang tayo ng rainbow when we are experiencing after rain, or when we are, for example, washing our car because we have water droplets. So in layman's term, magkakaroon lang ng rainbow after the rain. Or magkakaroon lang ng rainbow kapag may droplets of water. In many cases, you can see a second larger rainbow. It is the result of dispersion, refraction, and 2 reflections from the back surface of the droplet. So we'll not tackle about this anymore. Importante is you have the visuals of how rainbow is being made.